SCADA protocols have evolved over many years, always with the design objective of optimizing bandwidth and minimizing the impact on the hardware and RAM and ROM of the end devices. DNP, Modbus, 870-5 all do a very good job of this. These are designed around what have traditionally been the cost drivers in the system. Bandwidth was expensive, hardware was expensive, particularly in the embedded systems and the end devices. Over the years, since these SCADA protocols were developed, we've had some really radical changes in the bandwidth constraints. Serial technologies have moved from what were typically 1200 baud links some years ago to a minimum of 56 kilobaud. The LAN technologies have gone from the megabyte range to the gigabyte range, and we've developed a lot of new technologies like frame relay that really change the picture for substation communications. At the same time, we've also had even more drastic reductions due to standardization. Things like Ethernet and TCP/IP have really changed what computer communications is now. Because of this, we've had much expanded markets. Devices are communicating now that we didn't conceive of 20 years ago. Also, this same explosion has caused really major advances in hardware capabilities. All of this has basically reduced the cost of communications in terms of the bandwidth and the hardware. Because of this evolution of technology, we now have a wide variety of communications technologies available, and bandwidth is no longer the cost driver that it once was. The cost is greatly reduced. We can move an awful lot more information for the same dollar that we used to. We also, on the other hand, expect greater intelligence out of our substation applications, and that means that there's been an explosion in the amount of data that's monitored and moved around, and an explosion in the complexity of the applications. This means that the cost now is changing our focus from being worried about bandwidth constraints to being worried about how do we manage this huge data and how do we manage the data sets that are spread throughout the system that have to be configured, maintained, and updated in order to make all the applications work together. So we're shifting from moving data to managing data as the main cost driver in the overall substation work. As the volume of data has increased and the application complexity has gone up dramatically, we've now moved to higher costs for things like commissioning costs and commissioning both the end devices and the applications, maintaining the databases. Deregulation is added to this because there's a lot more data sharing now across organizational units, and that makes, again, this data configuration and management even more critical to the utility. Because traditional SCADA protocols were defined to move data with a minimum amount of overhead, the meaning or semantics of data as it's spread through the system has to be maintained in different ways. So typically you'd have configuration of RTUs and IEDs, configuration of databases, and configuration of applications that all have to be done to make sure that the right data is getting to the right place. So instead of moving phase A voltage from some particular line, you're moving point number 3850, and someone's got to figure out all along the system whether that point, as those point maps occur, that the right data is flowing in the right places. This validation is costly and time-consuming and requires a lot of staff time to be able to maintain this. These trends aren't specific to the utility industry. When you look at all of the communications world, we've moved towards more object-oriented communications capabilities or protocols that organize the data by function. This greatly simplifies distributed applications and managing the applications. Similarly, we standardize object models that allow for a high degree of interoperability between applications. And we also include things like self-description and metadata that allow for online validation. Now the concept of metadata comes from things like Corbo, where as the objects are moved around, you're not simply moving the bytes of data, but you're moving description to talk about type descriptions and allow for type checking as it goes along. and identification of data. The semantic meaning of data goes along with the raw data. This is basically trading off a little bit of bandwidth to allow for a higher degree of interoperability and validation of application connectivity. So it's an important piece that's, again, it's not specific to the utility industry. It's the way all of communication is moving, because really connecting the applications to the data has become a bigger chore than trying to buy the bandwidth to move it. So the previous generation of SCADA protocols were designed around the idea of optimizing bandwidth and processor loading while maintaining data integrity and reliability. These protocols like 870-5 and DMP, Modbus do a great job of optimizing these things. But the next generation of protocols, such as 61850, are trying to reduce the data management problem while also maintaining integrity and reliability. So they're really focused on different problems because the cost drivers have changed now over the years. To summarize then the design objectives underlying IEC 61850, when we set out to develop the standard, we wanted to address the data management cost drivers using modern communications techniques. We wanted to achieve a high degree of application interoperability using standardized object models. We also wanted to simplify substation engineering by using a common configuration language. This also addresses a lot of the data management issues. And one important piece to it is the online validation of the substation communications using both metadata and self-description. The self-description piece, we weren't looking to do plug and play, but we did want to be able to do online validation of everything. So basically everything that's described in the configuration language is also available through the underlying services. So you can find the object model of the device at the device. You can find the capabilities of the device both in the configuration files and in the end device through this self-description techniques. So this is an important piece that we can both configure these devices and then once they're operating, validate that they in fact are talking to the systems that they think they are and that the data is organized in the way that it's supposed to be. So it's both offline configuration and online validation. This is different than plug and play. We're really not interested in trying to get into plug and play issues within the substation, but we did want to be able to plug and validate. IEC 61850 was developed by 3 different working groups within TC57. It's working groups 10, 11, and 12. The 3 groups worked in task forces that spanned all 3 groups so that the work would be highly coordinated, and ended up developing really one document set. The work was derived originally by combining submissions from CGRE and the EPRI-sponsored UCA project. Most of the work is pretty much backward compatible with UCA. The scope of 61850 is much broader than anything that's been attempted before for substation automation. It spans all areas of the substation, includes multiple protocols for various special purposes. It has a large and extensible object model, including standardized naming and standard data types. It also has, for the first time, a standardized configuration language that can be used for all the devices in the substation.